we had this problem, and these were the Theorem Mountains of Mordor, and our friends Sam and Frodo were going to make their journey from the gold point. Sorry, a little fast. Let's see here. They were starting here, and they were going to make their journey from the gold point along this mountain ridge here up to the turquoise point there. And so we said that their path would be something like this. And we wanted to find, and so this was, they're moving through a vector field here, which is the gravity field, which is the force of gravity straight down as a constant force straight down in the negative z direction everywhere. That's what gravity is like, or the force of gravity. And so we were going to think about constructing a line integral over this path on this multivariable surface from the gold point up to the turquoise point. And so let's see, we said that was going to be our path C, but then we said that this surface was really complicated, really awful, and so parameterizing a path, making a vector function for that curve would be super awful, and we wanted to avoid it at all costs. So instead, we said, is there a different way we can do this? And we noticed that the vector field was a gradient field. We noticed that this vector field 0, 0, and then negative mg, we could write a potential function for that, whose partial derivatives were these components of this field. And because of that, our field is path independent. So we could get the same amount of work by doing a line integral over a different path. And so then the easiest would be to do the straight line path. And so then we parameterize that. Here it comes. So here over to the right there, we parameterize the path. We did our linear segment from one point to another, and then we set up the line integral, which would be the vector field f, or 0, 0, negative 75 times 9.8 dot dr. And so dr was the individual rates of change of each component of the r function, dt, and we came up with that for the line integral. And this would be the amount of work that the field does on Sam and Frodo as they walk. But then the work that Sam does would be, he's carrying Frodo, so that the work that Sam does would be equal and opposite to the work that the vector field does. And so we see the work that the vector field does was a negative 712, so the work that Sam does was a positive 712.95 kilojoules. Okay, so we said, okay, we could use path independence, that this is a gradient field, to avoid this awful vector function and just do the same line integral, or line integral for the straight line path, which is through the air and goes through the mountain, and that's no problem in a gradient field. It's path independent. And then we said there's another way to calculate work, and that's in a gravity field, and that's by difference of potential energy. So the formula for potential energy is mgh. So we could calculate mgh final for Sam and mgh initial for Sam, carrying Frodo. And we got the exact same value, the positive, because it's the work that Sam did, the positive 712.95 kilojoules. And then we noticed that our potential function was the exact same formula as the potential energy. That it was mgh is really the same as mgz. And so we said, by finding the difference in potential energy, we really also found the difference in the potential function from the starting point to the ending point. So those are kind of one and the same. So therefore we can write the line integral as the potential function evaluated at the endpoint minus the potential function evaluated at the start point, because that was one and the same as potential energy final minus potential energy initial. The formula was the same. And this conclusion was the fundamental theorem of line integrals. And notice we said we're in a gradient field, and so we have path independence. And notice how this other way of calculating the line integral has nothing to do with the path, right? So it kind of underscores this idea of path independence. It only has to do with the value of the potential function at the end and the value of the potential function at the beginning, and nothing about what's happening in between along the path. So that was where we left off last time. Any questions about coming up with the fundamental theorem of line integrals? All right, so let's take a look at our problem in the... Okay, so number 7 says we have the vector field x, y, z is the components of the vector field. And we're going to compute the work done by F on a particle moving along C, where C is this. C is according to this path, this vector function from 0 to pi over 2. So the work done, we know, is the line integral f dot dr over C. So we're going to rewrite, just like we've done line integrals, we're going to rewrite f, x, y, z, in terms of points on the curve. So what are x points on the curve? Always 1 plus 3 sine t. I'm going to use s and c as abbreviations for sine and cosine. And then 1 plus 4 sine squared t. And 1 plus 4 sine cubed t. And then dot dr. So dr would be the individual derivatives of the components. So 3 cosine t. This would be 8 sine t cosine t by the chain rule. And 12 sine squared t cosine t, again by the chain rule, dt. Okay, and so looking ahead here, we're going to do the dot product, and we're going to get here sine times cosine. Here we're going to get sine cubed times cosine, and here we're going to get sine to the 5th times cosine, plus other terms too when we multiply these by 1. So it's going to be a long trig integral. It's going to be a long trig integral that we're going to evaluate from 0 to pi over 2. So setting this up, that's good practice for line integrals, but solving it, no thanks, right? This is a lot of sines and cosines for 2, 4, 6, in fact 6 terms, 6 different terms to do antiderivatives of most of those, u substitution. So no thanks. Is there an easier way to do this?
Yeah. Potential function.
Okay, so can we use the fundamental theorem of line integrals?
Yes.
Why?
Is our vector field a conservative function or conservative field?
Is it a conservative field? So we got x, y, z. Is that conservative? Can we write a function f whose partial derivatives are x, y, and z? Partial with respect to x is x, partial with respect to y is y, partial with respect to z is z.
Yes, they also told us.
Yeah. So, and the problem even told us that, right? So they say find a function such that this is true. So that's assuming you can't ask that question unless it is a gradient field. But whenever your x component is strictly a function of x, and your y component is strictly a function of y. Christian, you turn your microphone off, please. Christian?
Yeah, sorry.
Okay. So whenever your x component is strictly a function of x, and your y component is strictly a function of y, and your z component is strictly a function of z, that will always be a gradient field. That will always be conservative, because you can simply take the individual antiderivatives, and it will work. Okay. It gets more dicey when you have crossover, right? When you have y's and z's here, and you have x and z's here, and you have x's and y's here, then sometimes it is, sometimes it's not. But whenever it's just a function of x, a function of y, a function of z, in that order, you'll always have a potential function. That'll always be a gradient field. And they said, we know there could be a constant, but that constant is determined by this, that when you plug in 0, 0, 0, you need to get a z value, or in this case a w value, so, right? You get some value of 0, and the only way that could be if you plug in 0, 0, 0 to get 0 is if c is 0 also. So we got a potential function. We have a gradient field, and since we have a gradient field, we can use it as an alternate way to do this line integral. What will we do?
Would we write x, y, and z in terms of t, and then evaluate from 0 to pi over 2?
Okay, you could do that. Yep. Or we could just, we know we're going to do f final minus f initial.
Yeah, don't even do an integral. Just plug in like the final and initial position.
Yeah, and how do we get the final and initial positions?
I think based on the t for curve C.
Yeah, so when t equals 0, this function gives us the initial position, x, y, z, right? Vector functions are curves, and they give, for every value of t, they get all the locations on the curve. So this is why this is x, y, and z. So when t equals 0, we get, this is 0 and 0 and 0, so we get 1, 1, 1. So this is for t equals 0. And then when t is pi over 2, what do we get? Pi over 2 makes sine 1. So this will be 4, 5, and 5. So when t equals pi over 2, we get the x, y, z point 4, 5, 5. When t equals 0, we get the x, y point 1, 1, 1. And so so now we're evaluating this in our potential function that we found, right? So we're going to evaluate 4, 5, 5 using the potential function, evaluate 1, 1, 1 using the potential function, and subtract. And that's the fundamental theorem of line integrals. And that will be the same as the work that you get from doing the line integral directly. Okay, so questions on that? Does it make sense? Any questions? Okay, so if this was not a gradient field, could we do this? Could we use the fundamental theorem of line integrals?
No.
No, because you can't find a potential function. If it's not a gradient field, there exists no function such that these are the partial derivatives. And so if there's no function, there's no potential function, then you can't do this, because this all depends on plugging in your starting and end points to the potential function. In terms of these multivariable functions, back when we introduced them, a month and a half ago, or so, maybe even longer, we said there were 4 representations. First was a formula, function formula. That's what we have here. What were the other? We had 4 representations of these. What were the other 3? I don't even remember.
One of them was a table.
A table of values. What else?
The contour plot or level
Level curves, contour plot, right? A contour plot of level curves. And what was the last one? It was the representation of a multivariable function. It's the graph. Remember what the graph is?
Or was that?
Surface in R3. If it was if it was if it was a two variable, it was z equals f of x and y. This was the most common ones we looked at. That was a surface, right? That's a surface in R3. So now, finding these, what are these? These are z values, right? Well, in this case, like w, but anyway, these are like dependent variables, the dependent values of the function. And all of these representations give ways of finding values of the dependent variable, right? The table is a table of, if it's a two-dimensional table, it's a table of z values. Right? The contour plot, those level curves, those are constant z values, right? Those are z values. The table gives values of z for different ordered pairs x and y. Surface in R3, that gives like ordered triples, right? Like ordered triples, so a z for every x and y. So in these problems, you might not always have the function formula to generate these function values to use the fundamental theorem. You might have a different representation to get these output values of the potential function. It might be a table, it might be a contour plot. So just remember that those are just different representations of the potential function. And you can pull off values of z for those and subtract. Get the final value of z, initial value of z, and subtract. And that might not always be using a function formula. Okay, does that make sense? Any questions on this? All right, well let's do another example of this, and then we'll summarize and we'll move on. So here is a couple paths through the vector field, and this is the vector field. One y. And I'm going to call this this path starting here from say 7.4 comma 0 to 0, 7.4. And this is like a parabolic path here, and we'll call it C1. So if I want the line integral from 7.40 to 0, 7.4, that would be the integral over C1 of f. And so C1, say, is R1. And we could parameterize that curve. We've done that lots of times before, but I'll just call it x1t, y1t for the components. And that will define all the ordered pairs on that curve. And then my vector field, I'm going to do f.dr. So remember, for doing a line integral, you're going to rewrite your vector field in terms of the components of your vector function that defines the curve, because we only care about xy ordered pairs along that curve, so that will be true. And so we do 1 comma, well, that would be y of t, y1 of t, dot dr, and dr will be the derivatives, so x prime 1, y1 prime dt. So we've had practice doing line integrals. We know how to do that. We rewrite the vector function in terms of our, we rewrite the field in terms of our vector function representing the curve, dot dr. So now I want to know, is there another way to get the value of this line integral? Is there another way?
We could see if it has a potential function.
Okay, right. So is this a conservative field? And let's use that other check that we learned last time. What was the check for if you have a vector field PQ? And how do we know if it's a gradient field? If what?
You can take the partial
Take the
derivative.
partial derivatives.
If what? If P with respect to
Y
y equals,
with respect to x.
because really what that's saying is Clairaut's theorem, fxy equals fyx. This is already the partial with respect to x, and then we're going to take a second derivative with respect to y. Vice versa here. So let's do it. So what is this with respect to, what's the rate of change with respect to y?
0.
And what's the rate of change with respect to x?
0.
0. Equal. Gradient field. So there must be a potential function. So this is a pretty easy one to figure out. What is the potential function? You really have, again, it's kind of like a function of x, function of y. And so we just do antiderivative of each and add them together.
X plus y squared over 2.
Yep. Now be careful, if you have y's in this function and x's in this function, you can't just take the antiderivative with respect to x, antiderivative with respect to y, and add them up. You got to check. You got to write out the function in two different perspectives and see if they can resolve into the same function. But when you have just a function of x and a function of y, it's pretty easy just to write it down like this. So we got a gradient field. So we know that we can use the fundamental theorem of line integrals. So this is going to equal what? F evaluated at which point?
7.4.
Final, yep, the final destination minus. And again, that's just a matter of using the function to find those z values, right? Okay, and so again, those are z values. And so z final minus z initial. So in a graphical sense, what is z in the graphical sense? So what is this z final minus z initial? This is just the plot of x and y, right? What does z represent in a in a visual sense here?
The height at a point of x, y.
Right. So now it's like, so far we've just been talking about like the force through this two-dimensional field. When you bring the fundamental theorem of line integrals into it, you kind of introduce a new dimension, right, into this problem, a third dimension. And so this ends up being, so then in the third dimension, what is z final minus z initial? What does that represent?
Change in height.
Change in height, good. The value of that line integral is really the change in height from what's so 7.4, this is x, and this is y. So 0.74 is here. It's this z value at 7.4. And then this z value is 7.40. And so this is z final, and this is z initial. And so the fundamental theorem of line integrals is really taking us to the third dimension and saying, what's the change in height of those z values? So what do we expect? Looking at the picture here, what would we expect for the final answer?
Negative value.
Yeah, because this is z final. It looks like z initial is greater than z final. So it looks like if we were to do the math and plug in x and y and evaluate, we're expecting less than 0 based on the picture here. Z final looks less than z initial. Okay, because those are really what? Z values on the potential function, which is That potential function is really the surface, right? It's really this x plus y squared over 2 is that gold surface. And so the fundamental theorem is really asking about what's the difference in z of the initial point and final point of points on a surface, an R3 surface. Okay, so going back to R2, what would be another way? I'm going to move this back to R2 again. What's another way to get the value of that original line integral that we were talking about? Which is along the red parabolic path. Close there. All right, we'll just call it a day right there.
Would you just be the opposite of the blue path?
Okay, so if our original line integral was from that point to that point, then what about in the blue? So we'll call, and that was C1. Now the blue path we'll call C2. So we could do the line integral over C2 of f dot dr. So we'd have a new path we'd parameterize. Okay, but both of these are, especially compared to doing the fundamental theorem, both of these probably would not be very, efficient or advantageous, right? This parabolic curve would be not simple. This would involve sines and cosines. And so, is there a path that's considerably more efficient and maybe starts to become maybe as easy as doing this, using the fundamental theorem, that would be much easier than C1 or C2?
It's just a straight line.
Okay, a straight line. But even a straight line takes a little work to parameterize, and you still have that line integral to do, and it's still going to be a lot more work than this. So is there another option? Can we be really creative here and think of a way? So so these are all equal. So let's call that C3 is the straight line from start to finish. These are all equal, right? So the original line integral is equal to the difference of the potential function, is equal to this blue line integral, is equal to the black line integral. We have path independence and the fundamental theorem, right? So as long as we have the same start and end point, we're going to get the same value of the line integral. But is there maybe another way that would make life, in terms of calculating an integral, make life a lot easier? There is. Can what's that?
Are you looking for a better path?
Better in the fact that it will make doing this integral a lot easier, yes. Any ideas?
Path that is orthogonal to the vectors, the vector field?
I don't think you can have one that's orthogonal to all of them because
If
we know the answer is going to be negative.
Yeah, and in constructing that path would be kind of ugly. It wouldn't be a nice. It wouldn't result in a nice, easy line integral. What would make a line integral? What makes integrals easier? What makes computations easy? When what happens?
It looks like the blue line is a circle. Is that something to do with the answer?
Well, the blue line is a circle, and that will involve cosine and sine. But I'm still going to have to create this whole thing and do this dot product and do a lot more work than this.
Is it when the inside is just like 1?
Okay, or what's even better than 1?
0?
0, right? When we get zeros, especially multiplied by things and adding things, it makes life computations really easy. Things cancel out. So what path involves 0 or zeros?
Would it be along the x and y axis?
What if we did a piecewise path along the x-axis? How would we parameterize that path? What would the parameterization be? What's true about every point, right? The parameterization of a curve or a line are all the coordinates of the points on that curve or line. The parameterization, what's that?
x0.
X is 0?
X comma 0.
Oh, x comma 0. Right. T comma 0. Yeah. Your y coordinate is always 0, and then we can just let x be t. And then what about along here?
Zero comma t.
0 comma t. So this, we'll call this C4. So this last one along the x-axis, along the y-axis, C4. And when you have one of your, even though you'll have two, we'll have to add two things together. Your y coordinate is 0, your x coordinate is 0 here. That potentially could make this the easiest of all these paths, because zeros, you're going to take the dot product, and that half the dot product is going to cancel out, and you have a very simple, right? You have a very simple, so it'll be t dot 1 comma 0. It'll be your f, or sorry, it'll be 1 comma y dot 1 comma 0. Look at that for that first part of the path, because y is 0. So your vector field is 1 comma 0. Your dr is 1 comma 0. So notice, super simple. So it's just something to keep in mind when you have path independence. Making your path part or all of your path along an axis can make the computation very much, very simple because of the zeros that you have. Okay. Any questions on the fundamental theorem of line integrals, path independence? So let's summarize. Let's summarize this stuff about conservative vector fields. Questions on this screen? All right. So here we go. Let's summarize right here. So I'm going to go too fast for you to be able to write all this down. It'll be in the video. So just listen. Conservative vector fields. The following statements are mathematically equivalent. That means if any one of these statements is true, then you can conclude all the rest are true. So f is a conservative field means that f is a gradient field. If it's a gradient field, it means it has some potential function f, such that the gradient of f is your vector field. Okay, Clairaut's theorem holds. This was where it all started. Every closed loop in a gradient field or in a conservative vector field has a zero circulation. Right? This is where we came from. Conservation of energy. The work around every closed loop has a net value of 0. Path independence. Given any 2 points A and B and F, the line integral will be the same regardless of the path from A to B. And then the fundamental theorem of line integrals says that the line integral from A to B is the potential function evaluated at B minus the potential function evaluated at A. Again, if any one of these is true, then all the rest are necessarily true. They're mathematically equivalent statements, all of them. Okay, questions on conservative vector fields, path independence, fundamental theorem of line integrals. Okay, so let's take a look at something. We'll switch gears here. Something called Green's theorem. So Green's theorem, here's the setup for Green's theorem. These are all the conditions that have to be met. You need a simple, let's draw a picture. You need a simple closed curve. Simple means that it never crosses itself. So here's an example of C. Okay, it makes a closed loop, and then that closed loop then creates an interior region D. So what's inside here, all the points inside the closed loop is called the region D. And it's in the plane, so it's oriented, and then the curve has direction so that the interior is on the left as we walk around. So which way do we walk around here so that the interior is on the left if we were walking on this curve?
Nice.
It'd be counterclockwise. So this is what we call positive orientation. Positive orientation is counterclockwise, or if you were to walk on the curve, the interior D would be to your left. And then this thing exists in a vector field. And so we'll call that vector field PQ. So that's a smooth, continuous field defined everywhere. So there's no holes in it. There's nothing tricky about this vector field. It's a smooth, continuous vector field everywhere. Then here's the conclusion of Green's theorem. It says that the circulation, and I could put a oops. So we could say this is a circulation. Try it again. Better, there we go. So the circulation integral around C is equal to the double integral of that region of this function qx minus py dA. So little by little we'll kind of explore the meanings of what's happening here, but just from a purely computational standpoint, we're doing the one side of the Green's theorem formula is the circulation around the boundary, and the other side is the double integral over the region D of this function qx minus py dA. So dA could be like dx dy, or it can be, if it's polar, it could be r d theta. So it's our standard double integral. Okay, so Green's theorem, this formula is really a version of the fundamental theorem of calculus. It's kind of like a stepping up one dimension, so somewhat stepping up one dimension, and kind of more like if you called the fundamental theorem a one-dimensional theorem, this would be like the two-dimensional version of the fundamental theorem. So let's see how it relates. So let's kind of break down the original fundamental theorem, and this may be a conversation you've never had before, but the integrand is a rate function. So this is the rate of change of f. Did you know that whenever you were taking a single integral, your function was a rate of change function? Rate of change function for some function f. And then when you multiply the rate times a little change in x, you get a little bit of f. You get a little bit of the quantity. And we saw this earlier when we had those multivariable rate functions. We did rate times dx times dy. And when we did that, we got a little bit of whatever the quantity was. And that quantity represented by f. So this is equals a bit of the quantity, a little bit of the quantity, right? When you do rate times dx. And then the integral means what? Accumulate all these little bits. From a to b. And so that gives you what? It gives you a net change of the quantity. Or a net change in the function f. So we start with a rate of change function. We take the rate times a change in x at a particular value. We take the rate times change in x, like it's a little bit of the quantity. And then as we go from a to b, we accumulate all those little bits up to get a whole net change in f. And notice what's on the other side. What is that? That's the net change in f, but it's just calculated a different way. right? So now this is as final minus initial. So both sides of the fundamental theorem are calculating the net change in some function f. The integral side is calculating it by summing up or accumulating little bits of the quantity f using the rate function. This side is just looking at the final value of f and the initial value of f and subtracting to get the net change that way. So that's kind of an overview of the fundamental theorem. And so then this side here, accumulating all the little bits. So if we could draw a picture here, there's the boundary. A and B is like the boundary. And then the interval is like the interior. So this is the interval. And that's like the interior. Right? And there's F. So here, what? We're traversing across the interval and we're adding up bits of change from A, starting at A and ending at B. Here we're just looking at, oh sorry, this would be the rate function, my fault. This is the rate function. Here we're just looking at the final amount at B and the final, so all we care about here is what's happening at the boundary, the final value of the function at B minus the initial value of the function at A to get that net change. So which of these sides, left side or right side, is accumulating little bits all across the interior? Is it left side or right side? Remember, this side is going around the boundary, the circulation around the boundary, and this is the double integral across the interior. So our integral in the fundamental theorem is accumulating bit by bit across the interior, which is like across the interval. So which does that apply to? Does that match up with the left or the right?
The left?
The right.
The right, because the interior is D. So everything's stepped up one dimension, right? So now here the interior was like this interval. Now the interior is this region. And so we're accumulating across the interior bit by bit, dA by dA, and this is something of a rate function. And then this is the net change at the boundary, right? So it's the net change at B, or the value of f at B minus the value of A. And so that, since it's dealing with the boundary of the interval, that matches up with this because it's the boundary of our region. So the accumulation of many bits of a quantity across the interior, calculated by rate times the little change in the independent, that's those two sides, is equal to the net change of the quantity associated with the boundary. So you have the net change from starting at, just looking at B and A, you can calculate the net change. And then here, the boundary then is the circulation integral, which is the boundary of D. Okay, so the moral of the story is Green's theorem is totally analogous to the fundamental theorem, like kind of stepped up 1 degree of integral. There's all this parallelism, so it's a version of the fundamental theorem.